Good day and welcome to the Innovative Mine Closure and Reclamation Parsons Best Practices Applied conference call hosted by Scott Harso. My name is Dora and I am your event manager. During the presentation, your lines will remain on listen only. If you require assistance at any time, please key star and 0 on your telephone and the coordinator will be happy to assist you. Also, please don't forget to join to the web portion of the call. I would like to advise all parties this conference is being recorded, and now I am handing over to Scott. Please proceed.
Thank you very much, Dora, and welcome everyone to Parsons' technical webinar for the month of July. I think we've got a great presentation for you. We've actually got a trio of presenters working together here today to bring you information about our best practices with regard to innovative mine closure and reclamation. We will have Michael Nahir, Jamie Kars, and Les Cordone all presenting today. Next slide. Give you a little information about our standard housekeeping items. As you heard, all your phones will be on mute. You can submit questions using the Q&A section of the WebEx screen. We ask that you would give us your name and location when you ask a question in case we need to follow up after the webinar is over. Mike, next slide. Or two. And we will give you an Mike, we're not seeing the slides advance. If you could advance a couple there. And meanwhile, I'll give you an introduction to our presenters. Mike Nahir is a director of Parsons Mine Closure and Reclamation Practice. He brings to us 27 years of experience doing assessment and feasibility studies, design, and closure planning of numerous mines in his portfolio. Jamie Kars is the Senior Program Director with Parsons, who has over 40 years of experience in doing mine work, especially in the northern areas of North America. He's been doing the work for Parsons, managing, developing our work at Giant and Faro mines for many years. And Les Cordone, for those of you who frequent our webinar series here, you may have heard Les in the past. He's been on several of our webinars. Les is Vice President and Manager of our Industrial Water and Wastewater Treatment Practice. He's bringing over 35 years of experience in industrial water and wastewater treatment systems around the globe. With that, I'm going to turn it over to Mike to pick it up with a Parsons core value moment.
Great. Thank you, Scott, and good day, everyone. I hope you can see the core value slide. Parsons has...
Still seeing the opening
Pardon?
slide, Mike. We're still seeing the opening slide.
Oh. Okay. Yeah, I'm not sure what happened there. My slides are advancing, so. You see the agenda slide?
No.
Okay, let's see here. See the agenda slide now?
Yes.
Sorry, forgive me. Okay. So I'll go through a core value moment. Then I will speak to mine closure liabilities. I'll go through key issues and considerations, mine closure and reclamation solutions, and then Parsons' approach, our business approach to that. Then Jamie Kars will speak to the Faro, both the Faro and Giant Mines, abandoned mines, as case studies. And then Les Cordon will finish with wastewater treatment solutions and Parsons' approach to wastewater controls. Okay, Parsons has 6 core values, and I will speak to the core value of integrity. In the field of engineering, we learn from the early days at university, where in the first year we watched the classic bridge failure video that makes the statement that lives depend on sound engineering, to the professional ethics exam to obtain our professional status. Every day we need to remind ourselves that in the face of competing pressures, the integrity of what we do is the most important of all factors that come into engineering design. Mine closure is a relatively new field, and sound judgment and integrity factors even more in how we practice the profession. For many mine owners, there's a significant financial liability due to unclosed or incompletely closed mine infrastructure no longer in service. In a number of those cases, there are site features requiring long-term care, such as water treatment or tailings dam safety. There are 2 main drivers now in play that suggest that owners need to deal with liabilities sooner rather than later. First are the high-profile dam failures that occurred in Canada and more recently in Brazil, where it led to loss of lives in the latter case. The second driver comes from the investment community wanting to distance themselves from the exposure of significant risks, as is pointed out in the yearly World Risk Report produced by the International Mining Journal. So now proper closure has become a top priority for mine owners. So what are the nature of those risks? The differentiator in mining compared to other facilities and contaminated sites is the massive volumes of waste produced, which one can imagine when removing ounces per ton of commodity per ton of rock. In many cases, this rock will contaminate water courses, which I'll discuss later. Usually most of the waste is stored behind tailings dams, which themselves are commonly located in water courses due to topography and design needs. For long-term closure considerations, high-risk tailings dams need to be built to withstand maximum expected seismic forces, as well as maximum precipitation to not fail. And these variables change over time as climate changes, meaning the service life of tailings dams need to be indefinite. Many of the surrounding population do not want the extensive disturbance to the land coming from the storage of these wastes. As a result, proper closure can be high in CapEx and OpEx. As an example of such challenges is the Faro mine in the Yukon Territory in Canada, which Jamie Kars will speak to. It's a large mine built and managed in the standard of the 80s, which produced lead and zinc. It was not built for closure, and now many upgrades are needed to all the mine infrastructure, including upgrading the tailings dams, diversions to meet seismic and hydraulic standards, and the tailings and waste rock that generate tremendous contamination in the water courses. The mined-out pit walls are unstable, and combined with the waste rock, the tailings areas take up an extensive part of the land area and valleys. So recently, there's been some effort to provide guidance for the management of mine closure for industry and governments. Most significantly, the International Council on Mining and Metals, ICMM, which is a mining industry association, has generated useful guidelines and tools to support proper closure, including best practices in stakeholder engagement and social closure. The International Standards Organization, ISO, is nearing completion of the Mine Closure and Reclamation Planning Standard and has accompanying technical guideline manual to support that standard. The International Committee on Large Dams, ICOLD, and the Canadian Dam Association, CDA, are excellent tools for designing and managing dam safety and are internationally recognized standards. They provide hydraulic and seismic design guidelines based on risk to population, the environment, and critical infrastructure. The common theme for proper mine closure starts with the main objectives that are set for the project, which would lead to the development of specific criteria in assessing and remediating for physical and chemical stability, as well as post-mining land use. These objectives typically involve the notion that public should always be safe from physical hazards on-site, including dams, slopes, mine openings, and other infrastructure. These objectives also include the need to protect the environment, particularly from impacts to surface water on the site and in the downstream receiving environment, and on land from eroding surfaces or blowing dust from tailings. Commonly, it is expected that after the completion of the closure project, most of the land should be left in a form which permits future uses such as wildlife, farming, recreational, or industrial development. The formation and buy-in to these objectives needs to be done with stakeholders and right holders to ensure success. I will talk briefly about the key physical risks that are the drivers for safety and environmental concerns. Tailings ponds are structurally the most significant risk. Many were built before real design standards were developed or were built with the mine operations design life as compared to a closure design life. Design considerations include maximum seismic stability, which would provide robust design requirements. Spillways need to be able to pass anticipated maximum predicted flows. Diversions need to be designed to pass those same flows. Stability of underground working, stopes, adits, shafts, and portals and pit walls are a significant safety and land use concern. Another quick word on tailings dams. Many dams have been and continue to be built on tailings as foundation, primarily due to lower construction costs and lower impact on operation schedule. The standard on this is changing, however, in favor of more stable and robust design approaches, such as centerline or downstream construction lifts. This can be a major cost item if upgrading is needed. In some cases, construction modifications, a change in operational requirements, or monitoring improvements can be efficiently brought to bear. We also need to consider designing to account for extreme events such as floods, earthquakes, as well as perpetual disruptive forces such as erosion and water infiltration that mine waste structures are subjected to. One of the big questions in the mine closure world is design life. Do you invest heavy in CapEx to design against all sorts of high consequence, low probability events? Or do you take the approach of lower CapEx with higher OpEx and hope that the OpEx reduces over time as technology improves? In some cases, the answer is already provided by jurisdictions as they standardize design requirements, but in many jurisdictions, this is left up to the owner as a financial decision, provided that they meet environmental regulations. Due to the durability of engineered structures and strengths of materials, it's hard to design for more than a period of approximately 100 years, certainly when you think about what we knew 100 years ago. We can, however, use projections, for example, based on the estimates of precipitation return periods to design for reasonably long periods, say up to 1,000 years, or even maximum precipitation estimates, essentially arrived at by extrapolating from what we know has occurred. There's obvious uncertainty in this approach as it is based on predictions. However, it is based on current science and updated regularly. So adaptive management is required, which I'll speak to later. To look at chemical concerns related to mine closure, you must look at the process waste streams, as well as environmental processes that impact valuable water resources. Process contaminants of concerns include mostly cyanide used for metals leaching, and mercury for old mines used to form amalgams. Acidification is common in pyritic host rock when crushed into sand-sized particles and then exposed to oxygen and water. This condition, however, can be a sleeper when the acid potential is greater than the neutralizing potential for many carbonates in the rock. Once the neutralizing potential is gone, the acids thus create a major challenge in future years. There are various tests that are available to determine this potential, and are used to base design decisions such as waste cover thicknesses, as well as source terms for water treatment if required. The holy grail, however, is to avoid long-term water treatment by getting ahead of it if possible and reducing the requirement for it otherwise. There are different processes to control reactions based on where you are in mine life. Addressing it earlier, of course, is better to be able to control the reactions. For example, covers are used to limit oxygen or water. Adding lime into the processed waste stream is another. Moreover, however, waste covers slow the reactions down in order to reduce any potential impacts to tolerable levels. Clean water diversions are used to separate fresh water from contaminants, eliminating or reducing the water treatment burden. And if you lose the battle, you'll need to treat until the reactions have been exhausted. The use of wetlands is an excellent way to reduce these costs by using natural systems of metals absorption. A very challenging part of mine closure is to manage the expectations of what the post-mining land use will be, as there will indeed be limitations. This is also the part of the closure work that stakeholders see and feel that they have control over, so it tends to attract a lot of attention. There are limitations to what you can do with large open pits, tailing storage facilities, and waste rock piles. There are creative ideas for large open pits, such as turning them into lakes and to be used as municipal landfills, for example. Tailings sometimes can be reprocessed for more value extraction or used as sand-like product for construction. For mines close to communities, waste piles can be turned into flat sports surfaces for soccer or other sports. The best case scenario is when you get the community involved to maintain the site for those recreational uses. This supports community buy-in and ownership. Another important consideration is to design the waste topography to matching surrounding landforms. It will support natural drainage and vegetation and thus require much less maintenance. Cost uncertainty is one of the greatest challenges in mine closure. This is a graphical depiction of the degree of cost certainty over mine life. The closure plan estimate is based on a conceptual closure plan with little engineering, and as a result, has a great degree of uncertainty. As production continues, variations to mine plans occur and need to be factored into the cost estimates. Progressive reclamation to close off any of the unused areas will reduce uncertainty and is encouraged by regulators. It is good practice to update the closure plan and costs on a periodic basis to reflect those changes. As more engineering is brought into the picture, cost accuracy improves. Commonly and unfortunately, actual costs can vary substantially from these estimates, as construction costs are quite price sensitive to the unit rates for high volume items such as borrowed materials. That if the quality and quantity of various borrowed sources are inaccurate, the cost can escalate in real numbers. Performance monitoring may require elements of rework and is rarely factored into cost estimates. There are, however, methods available to develop those estimates using risk tools like failure modes effects analysis or similar. So we find that the mine closure process requires the integration of planning and engineering with operations and construction management, all housed under competent project management, with the knowledge and skills to control all aspects of the job. Integration is required to have better alignment between these components so that it is possible to come out with an optimum solution that is cost effective. In developing the closure plan scope, the initial steps are to conduct the assessment and develop the conceptual site model. The challenge at this stage is to avoid turning every aspect of the assessment into a science experiment. Then going through an options analysis backed up by a multiple accounts analysis, comparing the performance against objectives. This requires a good cost estimate to ensure that the selected option is not unaffordable, thus necessitating a relook at the project objectives to see if they're achievable, and requiring more assessment work potentially. Looking at different failure modes will improve the design for robustness, as well as performing constructability assessments to ensure that you can build the project as planned to potentially expose hidden costs that are much better to know ahead of the construction work. Developing a well thought through adaptive management plan that will work through a process of addressing concerns in a systematic way will save from over-designing the project for risks that may never appear and then avoid unnecessary costs. As stated, project management is critical to the success of the project to incorporate the planning and design elements with construction management along with care and maintenance requirements. Cost and schedule control is a key to project success as there are multitudes of sub-projects. There are so many sub-project dependencies that if one of them is well off track, it will push the project critical path and increase costs. On behalf of the owner, Parsons typically does the procurement and manages all the subcontracts in order to have good schedule and cost control. Now I'd like to hand off the presentation to Jamie Cars, who will present aspects of the project and construction management of both the Faro and the Giant Abandoned Mines projects. Jamie?
Yeah, well, thanks, Mike. Good morning. As Scott noted earlier, I've been with Parsons for more than 30 years. And in that time, I've been fortunate to be able to pursue interesting work in the Arctic. In 2012, we identified an increase in activity at abandoned mines located in northern Canada. Many of these mines are the responsibility of the federal government, who, after years of assessment, had finally decided to undertake risk reduction projects under what they call urgent work programs. The first of the projects we carried out at these mines was the deconstruction of the roaster complex at Giant Mine, and that started in 2013. We were then awarded additional work at Giant Mine to do what they call interim construction management, which is the construction management of a number of discrete urgent work projects. In 2016, we were awarded a contract to manage care and maintenance of the Faro Mine at Faro, Yukon. Then back to Giant Mine in 2017, we received a contract to do the construction management of the remediation, which will hopefully see the closure of the mine site over the next 12 to 15 years. And in 2018, back at Faro, we won another contract to do the construction management work at Faro for the implementation of some urgent works at that site. Today I want to share some information and about some of the unique issues at both of these sites. The slide might be a little inappropriately named, not really case studies, but it's going to be an overview of some of the challenges at these mine sites. The first one's Faro Mine. The Faro Mine remediation project is considered to be the most complex abandoned mine cleanup project in Canada. The Faro site is presently in care and maintenance mode, with remediation projects being established with the goal of really minimizing or preventing the contamination of nearby land and water from the former mining operation. Faro is located in the Yukon, which is part of northern Canada. It's located on the traditional land of the Kaska, and it's located about 2,500 kilometers away from major population and supply centers. The climate is Arctic with long, cold, dark winters, cool summers, but we do get 20 hours of daylight during the summer. Most of the surface water is frozen from October to April, and permafrost is present at various locations. The Yukon features large distances and small populations, which can make it very difficult to staff and subcontract work. Parsons' role at the site is largely care and maintenance. The mine was abandoned in 1998. It's been in care and maintenance ever since. We're the fourth contractor to have this role. The work that we undertake includes monitoring environmental quality, managing clean water diversions, collecting and treating contaminated water, ensuring that the water leaving the site meets all of the environmental standards. We also maintain site infrastructure, include roads, bridges, buildings, dams, dikes, and stream channels. And as I noted earlier, in 2018, we also started doing construction management for some of the urgent works projects. So, Faro Mine was once the world's largest open lead zinc mine, and it's located in an area referred to by the Kaska as Sidzul, which they call the Mountain of Plenty, and it was well known for its abundant wildlife. There's a lot of First Nation activity in the area, primarily focused around sustenance hunting. The mine itself, or really the discovery, was found in the mid-1950s by some First Nation people who showed it to some prospectors. And afterwards, it went into development. It was actually constructed by Parsons in the 1960s, and it was operated until the late 90s. It's been in care and maintenance mode ever since as remediation plans are developed. Prominent features in the photo on the screen right now include the 4-kilometer-long tailings basin and its ponds, which is located in the center of the photo, the Rose Creek diversion on the right side of the tailings ponds, and the large pond that's really at the front of the slide is called the Cross Valley Pond, and it's the polishing pond used to store water on site, treated water on site before it's discharged to the environment. I want to point out X13 down at the bottom because we'll be talking about it on the slide now, what the Farrell Mine Complex is today. It is probably the most complex abandoned mine site in Canada. We're doing risk mitigation work at the site to ensure it remains stable and secure. And coupled with that is the environmental monitoring that ensures the systems are working as designed and we can minimize environmental health and safety issues. The realignment of the North Fork of Rose Creek is an urgent work project that's currently underway to prevent the creek from coming into contact with contaminated water. And I wanted to point out the Cross Valley Pond at the lower pond in the photo, that it was blue for decades until 2016, and it's reddy brown today, demonstrating just how site water quality is under constant threat. The water that was in that pond previously could be direct discharged to the environment 4 years ago, and now it requires treatment prior to discharge. In the foreground is the area of X13, which we'll talk about on the next slide. In 2017, the X13 area was a fairly quiet woodland. We had a weir in there, and we did frequent sampling as this was the down valley part of the tailings basin, and we needed to confirm water quality before it left the site. By May of 2019, next slide please, Mike. By May of 2019, upwelling impacted water from the tailings basin had resulted in degradation of the X13 water quality, and a capture conveyance system had to be designed, constructed, and placed into operation. Water from the X13 area is now pumped to the tailing basin and into the Farrell pit for eventual treatment. The project to capture and convey this water from the down valley area included the installation of 1,500 pumping horsepower and over 7 kilometers of insulated HDPE pipe. Farrell Mine has actually 3 open pits. The Van Gorda pit, which is at the top photo, was the site of the original discovery and presently contains some of the lowest quality water on site. The Grum pit at the bottom has relatively clean water in it, still requires treatment though, and we address that water by pumping it over to the Van Gorda pit and then treating that as one waste stream. The pit in the middle of the Farrell pit is the largest pit on site. It contains moderately impacted water because of its central location and its size. Most water on site is collected and pumped to the Farrell pit, and then we withdraw it from the Farrell pit for treatment and off-site discharge. The Farrell pit is the largest pit. It's approximately 100 meters deep. The water is 100 meters deep, and it contains a mixture of groundwater and the surface water recovered from elsewhere on the site. This is just a depiction of general water movements on site. Generally, we classify them as either clean water or impacted water. The impacted water, shown in green, is associated with all mining features, including the pit, the tailings, and the waste rock. There are some, it's mostly surface water. We do have some impacted groundwater in certain areas that we're beginning to collect. The clean water, shown in blue, is diverted around the mine site. Up at the north, we've got what we call the Northwest Interceptor Ditch. Across the upper right, top right, is the Farrell Creek diversion. Over on the right, sort of the lower right, is the Rose Creek. We'll be talking about that for a minute. I want to point out how the creek runs down toward the bottom of the slide, and then it goes through a rock fill, and then it comes out. Mike's gone to the next slide, so I wanted to show the general movements of water on the site while we've got the water capture treatment in operation. So the green arrows show the general direction of the movement of the contaminated water as we pump it up to the Faro pit, where we collect it, and then we run it into what we call the interim water treatment plant, the IWTP, and we do a direct discharge to the environment. We've got 2 water treatment plants working at Faro right now, and we're working on a third. The top photo is the interim water treatment plant. It was constructed in 2014. It has a flow rate of about 6,000 gallons a minute, and through that we process over 1.4 billion gallons annually. It's a seasonal operation that goes from spring up until about November. We have the Van Gorda water treatment plant. It was a legacy plant built by the mine operators. It was constructed in '92. It's got a 2,000 gallon a minute flow capacity, and we treat almost 1/2 billion gallons there annually. It's got a shorter operational season. It goes from about May until August. The photo at the bottom is the Cross Valley Pond Treatment Plant. It's presently under construction. It'll have a 2,000 gallon a minute operation, and it'll be seasonal as well. This is the plant that Les will be talking about in a few minutes. When you're in remote areas with small populations, it can be really challenging to staff projects and carry out work. And I did want to recognize the people that make it work for us. Faro's got a population of 344 people. Many of them work for Parsons. Our seasonal workforce reaches up to 50 or 60 people. And we have to do all services at site. We have to manage the site. We have to provide trades to do various maintenance operations. We have water plant operators, equipment operators, environmental techs, full-time chemists. We have site security, and we have to do all of our own emergency responding. Well, most of the activities we've talked about so far are about treating the contaminated water. We've also done projects to keep the clean water clean. This is a photo of some construction work we're finishing up right now. It's the culmination of nearly 2 years of construction in ice-rich permafrost to construct what they call the diversion of the North Fork of Rose Creek. On the upper right of the photo, you can see a bit of a rock fill. That rock fill used to extend across the creek valley, and we removed about 700,000 cubic meters of rock and then constructed this new diversion, the new channel for Rose Creek that runs through where the rock fill used to exist. This project is scheduled for completion in mid-October, and it'll be the first significant urgent work project completed at Faro. Okay, I wanted to talk about Giant Mine for a few minutes now. Giant Mine was in fact probably still is a large underground gold mine located in Yellowknife, Northwest Territories. Mining operations ceased in about 1998 when it went into care and maintenance mode, same year as Faro did. Giant Mine had started operation in the mid-40s. It was sidelined for a bit because of World War II, but it went into operation in 1948. Between 1948 and 1998, it produced over 7 million ounces of gold. And since 1998, it's been under a care and maintenance program administered by the federal government. Parsons has been active at the site since 2013. As at Faro, Giant Mine, we've had a number of different roles on site. We were doing construction there for a few years. We've done construction management for 3 years. We've been the mine manager since 2018. We're also doing care and maintenance since 2018. And we also have been awarded the contract to see the remediation of the mine over the next several years. That will probably go up to about 2030. The problem at Giant is arsenic trioxide. The bedrock in the Yellowknife area, including the Giant mine site, contains arsenopyrite. This naturally occurring mineral is composed of iron, sulfur, and arsenic. The arsenic trioxide waste was created during mining operations. When the ore was roasted to release the gold, arsenic was released as a gas. And as the gas cooled, the arsenic changed to a solid state and became toxic arsenic trioxide dust. The arsenic trioxide dust was initially released to the environment as shown in this undated photo. You can see the cloud, the plume coming out of the stack in the upper right-hand corner of the photo. As the years went on, this waste was eventually collected and it was stored in underground chambers. The roaster, as the complex was called, was comprised of 9 buildings and the large smokestack. In 2013, 2014, and 2015, Parsons decontaminated and deconstructed that entire roaster complex. That activity produced more than 10,000 cubic meters of arsenic and asbestos waste that's presently stored on site in storage containers. Once they started putting the arsenic dust underground, they pumped it into 11 chambers and 5 mined-out stopes that were built for storing the arsenic waste. Right now, those stopes store approximately 237,000 tons of arsenic trioxide waste. The chambers and stopes are surrounded by solid rock between depths of about 80 and 250 feet below surface. This model of the largest arsenic stope is compared to the 10-story building beside it. And it just shows the complexity, well, not only the size of the feature, but also the complexity with all of the different drifts and access points and things going into those into the stopes. The present plan is to take advantage of the subarctic climate and to freeze that arsenic in place. Parsons had a number of projects there. In addition to the roaster deconstruction, we've demolished several of the buildings, including what they call the C shaft, the H shaft. We've done projects to stabilize various features on sites, and we've also installed underground communications. At present, we're beginning the implementation of the remediation plan. Now I want to turn the presentation over to Les, who's going to take us back to Faro and discuss the design of the water treatment plant presently under construction.
Thanks, Jamie. I want to talk a little bit, this is just a few slides here, but I want to speak specifically about a project that's ongoing at Faro that Jamie alluded to, which is the treatment of the water from the Cross Valley Pond. You can go to the next slide, Michael. Interesting problem there. I got a phone call from Jamie, I think it was in 2017, that X13 area, which is the seep area, the photo in the inset on the upper left, they were having some issues. There was a territory discharge permit. And they were running into some challenges associated with whole effluent toxicity, specifically with whole effluent toxicity associated with rainbow trout fry. For the discharge going into Rose Creek, which is, as Jamie indicated, was bypassed around the valley there, and you can see it in the photograph. We thought about that a little bit, and I kind of went back to my experience when I was in undergrad doing acid precipitation work in the Adirondacks of New York State, where we had high concentrations of aluminum that was being solubilized by low pH water, and there was causing toxicity in fish gills, especially fry, where there's a high pH environment in their gill structure, and we would see something they would call clubbing of aluminum precipitation. And so we dug around and we actually found that, yes, it's a documented phenomenon that can happen also with iron. The photo down in the lower right-hand inset there is from a paper, and I provided the reference there. But that paper shows a micrograph cut of through a fish gill structure that has iron deposition in the structure. Basically, there's a higher pH environment there, especially in the young, the fry fish. And iron wants to precipitate when it comes into a higher pH environment. If it comes in and it's +2 state, it will want to precipitate as a hydroxide, and you get mucus formation, and you can have problems with respiration associated with the fish species. So we speculated that was the issue associated with whole effluent toxicity. We mobilized up and did a bunch of treatability work, jar testing, and then did some control studies to determine whether, if in effect, the presence of iron, which was present in anywhere from 10 to 40 milligrams per liter concentration, was potentially causing the whole effluent toxicity issue, and we basically proved that yes, it was of a concern. Fast forward a year after that, really, and we were looking at the Cross Valley Pond itself, no longer the seep area, but as you can see in that photo, the Cross Valley Pond, that's the pond that looks like it's got a lot of iron in it, as Jamie alluded to earlier. The seep water, basically, a lot of that comes from that pond. So now we have an issue with the potential of having to treat that water, since it's sort of the last line of defense for discharge of water. The water can be pumped back up to the pits, et cetera, but ultimately, at some point, you have to release water on your water management plan. So we were looking at what would we need to do if we had to treat this water. The iron was speculated as still being an issue associated with toxicity, although there was no iron limit in the discharge, just the whole effluent toxicity limit. But we also noted, and it's reasonable since this was a lead-zinc mine, that there were zinc concentrations in this pond that would be potentially problematic. The discharge limit is about a half a milligram per liter. So there was a solids issue that we needed to remove. There was zinc, and then we needed to go after the iron to reduce the whole effluent toxicity. This is basically simple type treatment, precipitation type treatment, but there's a few things I want to point out to you here that might be of interest if you are in this area. Iron is kind of the bane of a lot of groundwater treatment systems around the world because it's naturally occurring in groundwaters, often in a reduced form, the Fe+2 form, and as soon as it hits air or anywhere, it just wants to precipitate. It'll oxidize to Fe+3, and it'll precipitate as a hydroxide, and it'll cause fouling of equipment, activated carbon columns, all sorts of stuff. So it's problematic, and it's kind of tricky to deal with. The graph, you only need to understand the trend, but the graph in the lower left-hand of the corner basically shows the reduction of iron in a sample upon aeration. And it's starting at around somewhere in the 12 to 20 milligram per liter range, and it's ending up on the right-hand side at less than 1. But there's a time axis on the x-axis there that's over 40 minutes. That's 40 minutes of aeration, and the thing to note here is that the pH is at a pH of 7.5. Iron, if you look on the PC-pH curve, iron will have its lowest solubility, iron hydroxide, around that pH. But it just doesn't, the kinetics are very slow. So in this case, it's a 40 minutes worth of aeration. So if I'm going to treat 2,000 gallons a minute and I need 40 minutes of residence time, that's an 80,000 gallon tank, and then I'll need a backup one. So what we did was we did find that the kinetics can be improved by increasing the pH, and I don't show that here, but actually if we ran this reaction, which we did do at a pH of 8.5, the oxidation occurred in less than 6 minutes. So we utilized that approach as part of our design in order to save some money. The treatment system I'm going to show you here, you can go to the next slide. This is just a brief PFD. This is really simple metals precipitation type treatment system. We are repurposing 80% of the equipment that's used in this. We're reusing equipment that we were able to source from down in the States at another location that had only been in operation for 5 years. And so now it's up at site. I'll show you a photo of where we're at right now. The process flow diagram basically is we have on the left-hand side of the page there, we have aeration in an aeration tank that's about 18,000 gallon tank. That gives us the residence time that I was referring to earlier. We're going to add lime in that tank also, and we're also adding polymer in that tank to get both coagulation and to get precipitation of iron and coagulation. In this case, the presence of the iron helps us because we need the iron to remove to coagulate and flocculate the zinc and precipitate the zinc out. If we didn't have the iron there, we'd have to add a metal salt, either iron or aluminum. So the iron in this case is kind of a double-edged sword. We're precipitating the iron out in the first tank. Then it goes into a low mixing regime tank to flocculate, and then it goes into a standard inclined plate clarifier there where he's got the cursor. It's just gravity settling. The underflow from that clarifier ultimately will be pumped up to the upper reaches of the tailings area at the location, and then the final treatment there is just some multimedia filters. That's what Jamie had the photo of earlier, and those are repurposed multimedia filters. We need to get down to 15 milligrams per liter of TSS, and it would be tough to do that with gravity clarification consistently. So we had these filters that we could get for a really good price, and we're putting them in. You can go to the next slide. So here's a photo. Again, the location of this treatment plant, if you look at that photo again of the Cross Valley Pond, it's in the lower left, off the lower left-hand quarter in that general area. Very good. Thank you, Michael. That's where it's being constructed. The photo below is a photo of the treatment system in construction as of the end of last construction season. It's being built on rig mats, which is a drill rig mats, which is a common method of construction at the location up there and generally in this industry. And starting from the right-hand side, the two tall tanks there that are located out like right on top of each other. Yeah, those two tanks are the aeration tanks. From there, the chemicals will be added. It will go into the low mix tanks, which are the next ones right in there. And then they feed directly into the inclined plate tanks, which are just to the left of them. There's a frac tank in the middle. That's a brake tank that's going to be used as a pumping tank. We're going to repump, and then we're going to pump through those multimedia filters there. And then it will get discharged when we are discharging to that little feeder stream there that's going to take us right out into Rose Creek. We also have the ability to recirculate that back to Cross Valley Pond. It could ultimately go back up to the pit if we ran into problems, et cetera. So that's the treatment process. We're currently starting construction for this season. It'll be seasonally operated, just like the other treatment systems up there at site. Everything had to be designed so it could be drained, obviously, because we run into some serious weather conditions up there. And we're expecting to have it construction completed later this construction season and commissioned. And that's all I got.
All right, with that, thank you guys. Very interesting presentation. You did a great job. I want to use the next 10 minutes or so, open it up for questions. If you have a question, you can submit it on the Q&A section of WebEx, and we will get some answers for you. Dora, do you have instructions for them?
Yes, of course. So everyone, your question and answer session will now begin. If you wish to ask a question, please click on the three dots at the bottom of your page, select the Q&A tab, type your question, and click Send to all panelists.
All right. In the meantime, while we're getting some questions in, probably Jamie might be the best one, or Mike. Can you describe some of the difficulties you have doing the construction oversight and things like that because of the location, weather, and things like that for folks down here?
Yeah, thanks, Scott. It's Jamie. I can provide a few comments on that. It's a fairly challenging location just because it's remote and there's not a large population around. So it makes it very difficult to get contractors interested in the work, and it can be difficult for them to perform the work just given the supply chains and the lack of people in general, and in particular the lack of qualified people. A lot of the senior technical resources have to come in from southern Canada. So, of course, that takes time and it costs money. Since the onset of the COVID-19 issues, has been particularly challenging for us. because every person entering the Yukon Territory and also the Northwest Territory is required to go through a 14-day isolation period. So it's made it even more difficult to get people to the job sites.
See, we do have a question from John Miles, who asked, during the off-season or winter season when water treatment plants are off, what are the principal environmental hazards and how are they mitigated?
The hazards really remain the same. Our biggest hazard is the acid rock drainage and having this, what amounts to, low pH water with high zinc concentrations in it at the sites. A lot of that water is still in motion, so we do have to capture some of it year-round. An example is that X13 system that does operate year-round. We're putting in some other systems now that do operate year-round, particularly focused on some groundwater recovery and also recovery of certain parts of certain water courses. One of our hazards in the winter is the failure of a diversion when, like for example, we could get ice blockage or an ice jam or an overflow event or something like that that would typically see fresh water going where it's not supposed to go. It would get into, let's say, part of the site that maybe we've got concentrated, contaminated water, and it would dilute that, so it just give us more water to treat in the open season. And the other fear is that it might create a conduit for the dirty water in an area to escape. We've got several portions of the site where sometimes the dirty water is at a higher elevation than the clean water, and a little distance further on it can go the other way. So we can get clean water flowing into dirty water and dirty water flowing into clean water within maybe a couple hundred meters of a certain location. So we need to always be on the lookout for water going where it's not supposed to go, even in the middle of the winter.
And we see another question from Glenn Ulrich, who was asking, are there predictions on how long the water treatment systems will need to operate based on water quality monitoring results or other information?
They're still working on the actual, the design of the actual water treatment plant and trying to determine really how big it should be or whether there should just be one or there should be several. But the plans right now show that there'll be water treatment at Faro forever.
All right. Any other questions out there? Go ahead. One thing I did want to mention in the meantime is that this webinar has been approved for continuing education. So if you are in need of PDH hours for a PE or PG, feel free to just respond back to the meeting notice or send me an email, and we can get you the information, sign-in sheet, that sort of thing, and get a certificate processed and returned back to you. See a question from Trevor Sims. Can you discuss how much climate variation is designed in the context of climate change, precipitation, etc.?
I don't have much information on that. Perhaps Mike could elaborate on that a bit.
Yeah, good question. A lot of the design relies on understanding the hydrology of, what does the site need to pass by way of, maximum. For example, one of the design standards for high-risk dams, so-called high-risk dams, as developed through the risk system, that it would require be able to pass maximum precipitation. If it doesn't, if it's not able to pass that, then it can affect the integrity of the tailings dam. And the same goes with diversions. If diversions are around pits, and you may have overflow into the pit. So normally, and this is a bit where the art meets the science, is that you have to take some, do some risk exercises in order to be able to trade off robust design with costs and resources and maybe adaptive management systems going forward. So if you undersize, you might have to be in a position to do further design or in construction to upgrade or enhance the system's diversions or spillways. So that all gets factored in, and so typical designs use the best estimations on climate change and the impact on hydrology, but of course those are also location dependent and site dependent. So sometimes you'd have to do a lot of monitoring and then extrapolation, as I've mentioned in my talk, with respect to the amount of information we currently have and to design that into robust design.
And a follow-up question related to that, Trevor asked, what was the purpose of the diversion that you showed at the Rose Creek?
Oh, yeah, the diversion had a couple purposes. Go ahead, Mike.
Oh, you go. No, you go, please.
The diversion had a couple of purposes. One of them was that they created the diversion by placing about 180 feet of rockfill on top of Rose Creek. They were constructing a haul road that runs 11 kilometers down to the other half of the site. So that was used for all the mine traffic. Since then, the haul road has basically been essentially a filter on Rose Creek. It created what they call a head pond, a small lake on one side. The water trickled through the rockfill and then out the other side. So that was impacting the aquatic resources, and the First Nations were unhappy about that because it was disrupting one of their traditional gathering areas. So there was interest in removing the rock drain, as it was called, and joining up the two parts of the Rose Creek so that the fish could then spawn and continue their normal migration, which they hadn't been able to do for 30 years. There was also really a technical reason. There was impacted groundwater coming from higher up that was starting to seep into Rose Creek, which had been clean up to that point, and we were getting some elevated concentrations of zinc at certain low flow times, so it was representing a threat to the aquatic resources. So that was really I wouldn't say the second reason, that was another reason why the diversion was constructed. And the last reason kind of touched back to the question a minute ago about future events and climate change and things like that, is a lot of the diversions on site were built to lower standards. We've recently been upgrading some of them to 1 in 200 year events, but this diversion was rebuilt to 1 in 500 year event. So it was really an urgent early work type of project that was done for a number of reasons. Lastly, because it was inevitable, they had to upgrade the water course to the 1 in 500 just to protect all of the downslope tailings ponds in the event of future large storms.
All right. Mike, can you advance one more slide? I wanted to remind everybody that this is a monthly series, and we do have a webinar scheduled for August 12th. I hope you can join us. We have Robert Windle and Jeff Hong are going to be discussing the application of drone surveying and how to add value with drone surveying and sensing. So we hope everybody can join us for that. In the meantime, gentlemen, very good presentation. Really appreciate your time and your effort putting that together. And I thank everyone out there for joining us for this webinar. And with that, we will close things down. Thanks, everybody.
Thank you, everyone. This concludes your conference call for today. You may now disconnect. Thank you for joining and enjoy the rest of your day.